Hello everyone. In this video I'm going to solve this problem here. This is a problem from the qualifying exams, PhD qualifying exams, um, at the physics department in the University of Illinois Urbana-Champaign. And if I remember correctly, this problem was from the year 21, right? 21 UIUC PhD qualifying exams. So the reason I'm solving this problem and sharing it with you guys is that this problem really made me think about. I mean, it forced me to find a formal way to come up with normal coordinates. Right. So usually what do we do when we try to find normal coordinates is that we use the symmetry of the system and we try to guess, we try to come up with an ansatz. But here, the ansatz was a bit unorthodox. So I had to like formalize a way of constructing normal coordinates. So I'll show it to you guys, and we will try to answer all three questions A, B, C. And without further ado, let's get to the problem. So before that, let me describe what's in the question. So we have a system of three identical masses, right? They are connected using springs with strength K, which is defined by omega naught square m, right? And the masses are given by m. Spring constant is K, and it is also given that. So let me draw a diagram. Let's use a different color. So this one, next two, this next three, and they're connected using springs. Now assume that mass 1 is displaced from its equilibrium position by x1. This thing is displaced by x2, and this one by x3. All right. And also it is given that mass 1 is acted on by a force Ft, which is given in the question to be Fm cos of omega t, right? Okay, so so m is given, k is given, Ft is given, and x1, x2, x3, we know what they are. So it's also given that two of the normal coordinates are psi1 defined in this fashion, and psi2, which is this thing. Now it's really easy to see why these things are the normal coordinates. All you have to do is plug them in, right? Actually, if you want to see why these things are the normal coordinates, we need to come up with the equation of motion for the system for the all three masses. So we'll get to that now. So let's write down the equation of motion. So we'll use Newton's equation of motion. We don't need Lagrangian or Hamiltonian or any fancy tools. Newtonian is enough for this thing. So if we consider mass 1, for this f is equal to ma looks something like this. mx1 double dot as summation of all the forces that are acting on mass 1. So those are f of t, and as this string connecting mass 1 and 2 is stretched by x2 minus x1 amount, we have a force in the positive x direction of the following amount, kx2 minus x1, right? Now if we consider mass 2, its sequential motion is given by this. So in the right we have x3 minus x2, and in the left it's given by this thing, right? For mass 3, there's only one force acting on it, and that is towards the left, and hence given by this expression, 3 minus x2, which if we rearrange comes out to be x2 minus x3, and this thing turns out to be k x1 plus x3 minus 2x2, right? So we have equation 1, equation 2, and 3, right? So now it's quite easy to see why this xi1 and xi2 are normal coordinates. All you have to do is like, for example, let's consider this thing, right? To see why this is the normal coordinate, all we have to do is we have to minus 3, division 3 from 1. So if we do that, we have x1 double dot minus x3 double dot. This thing comes out to be, if I have to see, this thing comes out to be x3 minus x1 plus ft, and this is nothing but psi2 double dot, it's k minus k psi2, right, plus f of t. So this is the governing equation for the coordinate psi2, and this is uncoupled. UTLET, uncoupled, meaning this equation does not contain xi1 or xi3. We don't know exactly what xi3 is, but there's no xi3 here, xi1 here, so this equation is uncoupled. As a result, this coordinate xi2 is normal coordinates. Also, like similarly, you can find out why xi1 is considered to be. It's quite straightforward. So I'm not going to do that here. We have more interesting things to look at. So moving on, what we need to do right now is we need to find the coordinate, the next normal coordinate, xi3, right? So we need to find out xi3. What is xi3? So I'm gonna try to find this in a bit formal way. One could like use intuition and come up with an ansatz. You just have to observe how the system behaves, right? So I'm not going to do that here. I'm going to approach a bit mathematically. So what I'm going to do is I'm going to use the following logic. That is, if psi3 is a normal coordinate, then it's obviously a linear combination of the coordinates x1, x2, and x3, right? but we don't know what the linear combination is. For psi1, we know that is x1 plus x2 plus x3. For psi2, that is x1 minus x3, but we don't know what the linear combination is for psi3, but we take general coefficients, and they are a, b, and c, right? We need to find out what a, b, and c are. So if psi3 is the normal coordinate, then this is the linear combination of x1, x2, and x3. And also, what needs to happen is if, like, we're going to use equation 1, 2, and 3, right? And we're going to do this thing, that is from equation 1, we rewrite, we have one, or I could just let's see if I can copy paste this thing here. My bad. Let me retry. Let's see if I can move it. Yes. Yeah. Done. So we have this these equations, and now what we're gonna do is we're gonna like modify all three equations and multiply equation 1 with a, multiply equation 2 with b, and multiply equation c with 3 with c.